So let's look at titration curves. Remember with the titration, you're going to start with something in a flask. Well, the thing in the flask, it'll say like titration of a strong acid. The of part, that's what's in the flask. So in this case, it's a strong acid. So I've just got this liquid. That's the strong acid part. And then you're dripping in the base. In this case, it's NaOH, but it could be any base. And then across the bottom is the volume of the base you're dripping in. Now, what I just circled here, that's the initial acid concentration is 1. It makes sense that it's 1 because it's starting off with just acid and no base in it. So it's a strong acid. That's a good number for it. All right, so as you drip it in, so you can see the base, there's more and more and more base. Eventually, it's going to come to a point where all of the base have an equal number of H's to match up with, and they neutralize the solution. And in this case, it was at 25. So then you have this middle section here, and it's really tends to be a large section. Notice that it's right in the middle, the pH is 7. So there's no more volume being added. It just shows you that it does a very short pH change, and that's because all the H's are gone. That you started with all those free-floating H's, and they're all completely gone. And then the curve will continue on. You can add more base, but all the H is gone. So that's why the solution ends up basic, because all you've got left is now you're putting in base and there's nothing for it to interact with. And it makes sense for the base to be this value, this strong base value of, above 12. That's a good strong base value. So they all have, the strong acid, strong base ones always have this really long range where it's vertical. All right, now let's look over at titration of the weak acid. Still the same idea. You got the acid inside, you got the base. But notice that the pH of the acid is higher. So that makes sense because it's a weak acid, so it's not quite as acidic. And then you'll see, of course, we started at 0 base because we haven't added anything in. But we're about to start adding in base. And you can see, like, as we go along, we'll add more and more and more base. And again, you get to a point where all the H's have been neutralized by OH's. And so then we have this shift, again, this vertical shift, and in this case, it happened at the same volume. But notice that the equivalence point is 8.72. So it kind of makes sense because the acid wasn't as acidic, but the basic is really strong. So that equivalence point is going to be a little closer to the base side of things. And like before, when you keep adding and adding more and more base, it's just going to end up with a basic value. Notice that they actually end at the same value. So if this was the same base, they'll end at the same value. Now, when you have something weak involved, it's got a little bit of a shorter range where it has that pH that does, the change really fast. Like it happens in a shorter range of values than the strong one. So if you're trying to figure out which is which, the shorter range, that one's the one that's going to be the weak acid and the strong base. Notice again, it's the bottom section is how many milliliters have been added in. Now we're going to look at the titration of a strong base. So it's kind of like we're going to be starting opposite. We've got our flask, but now our flask has a base in it, and we're going to be dripping in acid. So the pH that you're going to start with, it's going to be a basic pH, in fact, a strong base pH. So it should be a really high pH that you're starting with. So it could be like maybe 12.5 or something like that, just something really high. And that makes sense because it's a base. It doesn't have any acid added yet. And across the bottom, it's going to be volume of like HCl. I'm just randomly picking HCl. All right, so as we add HCl, you're going to see our titration. It's going to eventually end with being around 1, and that makes sense because it's a strong acid. So it's going to have kind of a similar look, a really sharp plunge in the middle, and then we're going to end up over at our acid pH. And you'll notice, like before, you had this wide range where the pH basically jumped really fast, and it should fall at 7 because it's a strong acid, strong base titration. And it's very similar to the one above it. It's kind of like it's the inverse of it or the mirror of it in a way, if you want to think of it that way. And then if we do a weak base, you'll notice our weak base should not be 12.5, but like at 9-ish. So we're going to start there. And then we still should end up at 1 because we've got a strong acid. And the weak bases, they have a little bit more of a curve to them than the strong ones. And so as you're watching it kind of curves a little bit. It's always hard to kind of draw on these. And then you have your section that's a little bit more vertical. I should have made that a little bit stronger. It's a little bit more like that probably. And then you've got your short little equivalence area. And then this makes sense that this falls around, I don't know, like something acidic. Like maybe that's like something, maybe it's fire or something. But the other two things to look at is we're going to look at indicators and we're going to look at something polyprotic. So remember the polyprotic acids? Those are the ones that have lots of H's and they lose them one at a time. So it's not a strong acid, so we're going to just have it start at 3 randomly. And as it reacts with base, it's going to lose that one H. So it's kind of going to do a vertical section and keep going. And then you're going to have another reaction with that H2PO4 minus, and it's going to lose another H. It'd be like HPO4 2 minus. And so there it goes through another hump, and then again you can lose it again, HPO4 2 minus, and you're going to end up with PO4 minus. So you can kind of see you've got 3 different places that you can lose your H's when you're looking at this. So you know that these are polyprotics. Anytime you see lots of these like vertical sections, you can tell that it's something that's polyprotic. And it kind of makes sense. It's at 3. And it's going to start, and as you go along, in this case I've done a weak acid and it's base that's being added to it. Okay, so now let's look at the indicators. So indicators are things that change color at a certain pH. So if you choose the right indicator that has a pH change right around where your acid base should change pHs, you can visually see what's going on rather than trying to run it to an instrument on a different floor and get it in the instrument and everything. It's always nice to see things visually. This is the most common one. This is phenolphthalein. It's got to change around like, 9, 8, 7, whatever. So let's go and look up over here at a strong acid, strong base. Here's our pH changes at 7. So because it has that wide range, and we tend to pick one that changes like near the top of the vertical section. So that's going to, in that range right in there, something that has a color change in that range would be really good because it'll just take one drop for it to show that it's completely out of acid for the reaction. So something that matches around that phenolphthalein, it fits in really well. So that's a nice kind of a indicator when you're doing those kinds of titrations. Now in reverse, if you're starting with let's see, the weak base one over here, you'll notice this one has an acidic pH change, like say maybe that's around 4 or 5. I had said that before. When we look over at our indicators, if we try to find something that changes around 4 or 5, it's going to be, this is a really popular one, methyl orange is a really popular one for that indicator right there.